Good day, everyone. My name is Ayan. Good day, everyone. My name is Ayan Wata, and we are the Group 3 presenters, and we are tasked to make a pre-recorded lecture about the topic unsaturated hydrocarbons, including the alkenes, alkynes, and aromatics. So, to begin with this lesson, we should be able to know the intended learning outcomes, which at the end of this lesson, we should explain the unsaturated hydrocarbons, determine the structural formula, constitutional isomerism, nomenclature, cis-trans isomers, and polymerization of alkenes. Determine the nomenclature and reaction of alkynes and aromatics. So unsaturated hydrocarbons are organic compounds that are entirely made up of carbon and hydrogen atoms and consist of a double or a triple bond between two adjacent carbon atoms. And examples for this are the alkenes and alkynes. So what is alkenes? Alkenes are hydrocarbons which contains of carbon double bonds. Their general formula is CnH2n for molecules with one double bond and no rings. Alkenes are also known as olefins after the original name of for ethane or olefiant gas. So when the group of atoms that make up the molecules of different isomers are bonded together in fundamentally different ways, we refer to such compound as constitutional isomers. So for example, for this, the C4H8 alkenes are also known as the 1-butene, along with CH2 bounded to CH, CH2, CH3, known as the 2-methylpropene. The CH3, 2C bounded to CH2 are the constitutional isomers.
Next is isomerism. Isomerism is the existence of compound with the same molecular formula but different in structural formula. Chemical compound that have identical chemical formula but differ in properties and the arrangement of atoms in the molecule are called isomers. There are two primary types of isomerism, which are structural or constitutional isomerism and stereoisomerism. But in this discussion, we will only talk about constitutional isomerism and its different types, which are the positional isomerism, chain isomerism, and functional isomerism. Constitutional isomerism is the different compounds that have the same molecular formula but differ in their connectivity. That is in the sequence in which their atoms are bonded together. For the first type of constitutional isomerism, we have positional isomerism. Positional isomerism are constitutional isomers that have the same carbon skeleton and the same functional groups, but differ from each other in the location of the functional groups in the carbon chain. In order for us to identify if it is a positional isomers, the compound should have the same molecular formula and same chain length. For example, we have here two alcohol compounds. The first thing we need to do is to get their molecular formula. For the first compound, we have C3H80 as their molecular formula, and in the second compound, we also have C3H80IO as their molecular formula. And next, as what I've said earlier, a positional isomer should have the same molecular formula. And in this example, both of them have the same molecular formula. Next is that they should have the same chain length. In the first compound, we have 3 parent chain carbon atoms, and in the second compound, we also have 3 parent chain carbon atoms. Now we need to look at the position of the OH atom. Both of the OH atoms are located in different position. As we can see here in the presentation, the OH is located in the karian part, and then dirian po na part ang OH is located downward. Therefore, these two compounds is a positional isomers. For the next example, we have 1 butene and 2 butene compound. The first thing we need to do is to get their molecular formula. The molecular formula of 1 butene is C4H8, which is the same to 2 butene C4H8. The next thing we need to do is to get their carbon parent chain length, which the butene 1 has 4 carbon parent chain length which is the same to 2 butene, which has 4 carbon parent chain length. Lastly, their location should be different. In compound 1, the alkene group is terminal, and in 2 is internal. Thus, the butene 1 and the butene 2 is a positional isomers. Next is skeletal isomerism. Each C atom in the double bond contains the same functional groups and belong to the same homologous series but differ in the carbon skeleton. They have the same chemical properties but different physical properties. For example, we have here the compound C5H12. So C5H12 has three different structure. This one, the pentane, methylbutane, and 2-dimethylpropane. So for the first structure, it has 5 longest continuous chain of carbon atom. For the second structure, the 2-methylbutane, it has four longest continuous chain of carbon with CH3 attached to it. Then for the third structure, we have 2-dimethylpropane that has 3 longest continuous chain of carbon atoms. All of these isomers have the same molecular formula. As you can see in the structure, all of the compound possess 5 carbon atoms and 12 hydrogen. But all of these have different numbers of their carbon skeleton. In pentane, there are 5, 1, 2, 3, 4, 5 carbon skeleton. In methylbutane, there are 4, 1, 2, 3, 4 carbon methylbutane. And for the dimethylpropane, there is 3 carbon skeleton. But what is the difference between skeletal or chain isomer to positional isomers? In skeletal isomers, they have different number of carbon skeleton, while in positional isomer, they have the same number of carbon skeleton. The last type of constitutional isomerism is the functional isomerism. Functional isomerism are the constitutional isomers that have different functional group but have the same molecular formula. There are different classes of compounds that exhibit functional group isomerism. For example, we have alcohol will have functional isomerism with ether. Aldehyde will have functional isomerism with ketone, and carboxylic acid, 2-ester, and alkene and cycloalkane. For example, the chemical compound of ethanol. Where is it? Sa ethanol. We need to first change the functional group of the isomers. We need to reorder the atom. So for the chemical reordered atom, COC2, it can be reordered to CH3OH3, and it can be turned to CH3O3 to as ester as their new functional isomerism.
The alkenes nomenclature, the IUPAC system for alkene. So step 1, name the longest chain that contains the carbon double bond. Use the IUPAC root and the "-ine" ending. Replace the alkane suffix "-ane" with the suffix "-ine." Select as the parent carbon chain the longest continuous chain of carbon atoms that contains both carbon atoms of the double bond. Number the parent carbon chain beginning at the end nearest to the double bond. If the double bond is equidistant from both ends of the parent chain, begin numbering from the end closer to the substituent. Give the position of the double bond in the chain as a single number, which is the lower numbered carbon atom participating in the double bond. Next slide. Next is use the suffix diene, triene, tetrene, and so on when more than one double bond is present in the molecule. Do not use a number to locate the double bond in unsubstitute cycloalkenes with only one double bond because that bond is assumed to be between carbons 1 and 2. In substitute cycloalkenes with only one double bond, the double bonded carbon atoms are numbered 1 and 2 in the direction clockwise or counterclockwise. That gives the first encountered substituent the lower number. In cycloalkenes with more than one double bond within the ring, assign one double with numbers 1 and 2 and the other double bonds the lowest number possible. The next. So these are the prefixes of the carbon number of the carbon atoms.
Cis-trans isomerism. Cis comes from the Latin word that means on the same side, and trans is a Latin-based prefix that means across or opposite. Cis-trans isomers are stereoisomers, that is pairs of molecules which have the same formula but whose functional groups are in a different orientation and three-dimensional space. Cis-trans isomerism, also known as a geometric isomerism or configurational isomerism. This is a term used in chemistry that concerns the spatial arrangement of atoms within molecules. So how do we know if alkene has a cis-trans isomers? Consider the longest chain containing the double bond if two groups are attached to the carbons of the double bond or on the same side of the double bond. The isomer is a cis-alkene. If the two groups lie on the opposite sides of the double bond, the isomer is a trans-alkene. So again, an isomer is a cis-alkene if the bonds are on the same side, and if the trans is on the opposite side, that is a trans-alkene. Now, why can alkenes form cis-trans isomers? Cis-trans occur whenever both double bond carbons are directly attached to a carbon and a hydrogen. In this case, interchanging the substituents of one of the double bond carbons creates a different isomer.
Polymerization is a process by which Polymerization is a process by which an organic compound reacts with itself to form a high molecular weight compound composed of repeating units of the original compound. The polymerization of ethene by an ionic or free radical reagent AB is an example. The most important commercial reaction of alkenes alpermization. Polymers are macromolecules in which small units referred to in general as monomers are repeated again and again, derived from the Greek word monos meaning one and meros meaning parts. Polymers are huge molecules, so their molecules formulas are not written. Derived from the Greek word poly meaning many and meros meaning parts. A polymer is as different from its monomer as a long strand of spaghetti is from a tiny speck of flour. For example, polyethylene, the familiar waxy material used to make plastic bags, is made from the monomer ethylene gas. Next, alkenes and substituted alkenes form in addition polymer. An addition polymer is a polymer in which the monomers simply add together with no other products formed beside the polymer. Addition polymerization is similar to addition reaction described previously, except that there is no reactant other than the alkene or substituted alkene. Next. So, in addition, polymerization, the monomers add to one another in such a way that the polymer contains all the atoms of the starting monomers. Ethylene molecules are joined together in long chains. The polymerization can be represented by the reaction of a few monomers. Next one. So the bond line extending at the ends in the formula of the product indicate that the structure extends for many units in each direction. Notice that all the atoms, 2 carbon atoms and 4 hydrogen atoms of each monomer molecule are incorporated into the polymer structure because displays such as the one above are cumbersome. The polymerization is often abbreviated as follows. Next one is during the polymerization of ethene, thousands of ethene molecules join together to make polyethylene, commonly called polyethylene. The reaction is done at high pressure in the presence of a trace of oxygen as an initiator. Next. Many natural materials, such as protein, cellulose, and starch, are complex silicate minerals, are polymers. Artificial fibers, films, plastics, semi-solid resins, and rubbers are also polymers. More than half the compounds produced by the chemical industry are synthetic polymers, so some of the common addition polymers are listed in the table. Note that all monomers have carbon-to-carbon double bonds. Many polymers are mundane. Examples are plastic bags, food wraps, toys, and tableware. But there are polymers that conduct electricity, have amazing adhesive properties, or are stronger than steel but much lighter in weight.
Alkyne. Let us define first alkyne. Alkyne is an acyclic unsaturated carbon that contains one or more carbon-to-carbon triple bonds. Its general formula is CnH2n minus 2. Nomenclature for alkynes. The rules for naming alkynes are identical to those used to name alkene, except the ending YNE is used instead of ENE. When naming alkynes, we can still follow the same rules for the IUPAC nomenclature for alkanes. First step is identify the parent chain. Second, identify the substituents. Then, number the parent chain giving the triple bond the lowest locant. And last, put everything together having the substituents in alphabetical order. However, there are two main differences that need to be considered when naming alkynes. This is that the longest chain must include the triple bond and change the suffix in the parent chain from ENE to YNE. Now let us go on to alkyne reactions. There are three different alkyne reactions: addition, deprotonation, and oxidative cleavage. First is addition. Addition is the main pathway found in reactions of alkynes, and it is the breaking the E to C bond and form two new single bonds to carbon. The product of an addition reaction to an alkyne is alkene. Alkene reactions undergo additional reactions too. However, the upshot of this reaction is that alkynes possess bonds. One must always be alert to the possibility of two additional reactions occurring. Second is deprotonation. It is another reaction that is not present in alkenes. And take note that alkynes are more acidic than other hydrocarbons, that it leads alkynes to its conjugate base, an acetylide, which is an excellent nucleophile. The last reaction is oxidative cleavage. This is the treatment of alkynes with either ozone or potassium permanganate that leads to carboxylic acid. Aromatic. Aromatic hydrocarbons are compounds that contain sigma bonds and delocalized pi electrons between the carbon atoms in the ring form. If the Huckel rule is followed, a hydrocarbon can be an aromatic compound. This rule states that a compound is aromatic if it possesses the following distinct properties: tonality, the localization of the pi electrons in the carbon ring entirely, and a compound having 4n plus 2 pi electrons in its structure where n is an integer. Now let us go on to the nomenclature of aromatic. First, name the substituent followed by the name benzene. And then after that, if there are more than one substituent present, indicate the position by number followed by name of the substituent and name benzene. There's no need to indicate the position if there is only one substituent. Take note that positions 1, 2 are also known as ortho positions. Positions 1, 3 are also known as meta positions, and positions 1, 4 are also known as para positions. Lastly, the chemical reactions of aromatic hydrocarbons. Benzene undergoes substitution reaction instead of addition reactions due to the localized bonding system. There are two important types of substitution reactions for benzene. It is the alkylation, which is substituting an alkyl group into something, and halogenation, it is the replacement of one of H atoms in benzene for a halogen atom.
And that's all for this lesson. We hope that you have learned something from our report. For further knowledge about unsaturated hydrocarbons, you may vary from the reference link presented in our PowerPoint presentation. Have a great day, enjoy studying, and God bless us all.